Hello, my name is Elissa. Over the past year, I have worked on a project with Dr. Andrew Petruska regarding a new nonlinear control paradigm he is developing that uses a smoother and observer to plan a path from one point to another. The basic principle of this nonlinear control is as follows. If you start at a point A and move to some point B, you can look back and describe what you used to move from A to B. This observer sets a point A to be the current position of the robot and point B to be the desired position, and then calculates what steps it would have had to take in the future to move from point A to point B, and then applies this. The robot then uses a smoother which iteratively calculates the difference between the robot's estimated position and where it actually is, and tries to minimize that difference while moving towards its goal. This control paradigm is extremely versatile and designed to work for many different applications. The part of the project I specifically worked on was implementing this control system on an obstacle avoidance problem. For the obstacle avoidance algorithm, the observer system employs a cost function that is inversely related to the distance the robot is from an obstacle. This cost is based on the superellipsoid equation, which is used as a bounding box for the robot, and the cost increases once the obstacle moves inside or closer to the superellipsoid. The control system attempts to minimize the cost function by maximizing the distance from the obstacle while employing the observer and smoother to reach its destination. Once the obstacle avoidance is implemented in ROS, simulations are run to show the functionality of the obstacle avoidance. These simulations were run on a Husky robot in Gazebo, which is shown in Figure 4 in the top right. The obstacle avoidance was implemented as a model, along with an LQR model that calculates the dynamics of the robot, and a saturation model that limits the control inputs, which are linear and angular velocity, beyond a certain threshold. I changed the relative weights of importance of the avoidance model, labeled PFA in Figure 3, to show the effects of the obstacle avoidance model. As you can see in Figure 3, the simulation was run where the final destination, or desired point, was set to 4, 0, and the obstacle was set at point 1.5, 0.5. The obstacle avoidance was given different weights, so the higher the weight, the larger influence the obstacle avoidance would have on the model, and the higher the cost function would increase as proximity to the obstacle decreases. As you can see in Figure 3, where the weights of the obstacle avoidance model were increased, the robot made a more drastic movement away from the model as the intensity increased, and when the intensity of the obstacle avoidance model was 0, there was no effect, and the robot does not move away from the obstacle. In Figure 2, you can see how the smoother and the cost function behave as the robot travels to its desired point. The top plot is that of the cost function. It increases as the robot drives closer to the obstacle and decreases as it drives past and away from the obstacle. The second graph is the distance from the robot to the obstacle. The third and fourth plots in Figure 2 show how measured velocities adjust to the input control velocities, which is done by the smoother. One of the downsides to this model is that the robot will move away from an obstacle that is not in its path. This can be seen in Figure 1. The size of the line in Figure 1 is the width of the robot, so the robot would have not hit the obstacle had it kept its initial trajectory straight forward, but the obstacle avoidance model tries to minimize the cost related to the distance between the robot and the obstacle, so the robot moved away from the obstacle. A way that this could be improved is to use a cost function that is based on time to collision. This method could use current position and velocity and base the cost function on the time until the robot will collide with an obstacle. This way, if it is moving away from an obstacle or just driving next to it but won't hit it, it doesn't bother moving away from the obstacle. This project has a lot of potential applications, including self-driving cars, navigation in confined spaces, or even planetary or moon exploration, which is pretty cool. I enjoyed the opportunity to be a part of this project.